So this morning, our first outgoing fellow presentation is from Benjamin Reichelt. He is doing his graduate work at Massachusetts Institute of Technology, and he did a practicum at Los Alamos National Laboratory in 2022. I'm going to let him introduce his talk all by himself. So, thanks.
All right, thank you very much. So my name is Benjamin Reichelt. I'm a graduate student at MIT. I'm going to present some of my graduate thesis work, which is about exploring impacts of kinetic effects on inertial confinement fusion experiments. I'm planning on defending my thesis on September 4th. My thesis advisor is Chi-Kong Lee. And what I have here on the first slide is a picture of some burn histories from some experiments where we see the time of peak nuclear emission move earlier for a separated reactant experiment, which is indicative of kinetic effects, which I'll get into more later. Is this the wrong one? Oh, wait, which one of these did that? Okay, so I'd like to thank my collaborators and sponsors for this work, including, of course, the NNSA for funding me through this fellowship, the SSGF. So this talk is going to discuss two of my projects, which are tied to a couple of papers and invited talks, but there's a couple of other projects that I won't have time to get into. So as the outline, I'm going to start by talking about observation of kinetic mix enhancement and shock-driven implosions. And then I will talk about measurement of multi-species plasma effects using ultra-fast single-crystal diamond detectors, and I'll get into what all of that means in a bit. So starting with kinetic mix enhancement. As a summary, a separated reactant implosion campaign at the Omega Laser Facility has shown indicators of kinetic mix enhancement. Shock-driven implosions of separated reactant targets enable the study of kinetic mix. The nuclear bang times for the separated reactant experiments are about 50 picoseconds earlier than for the control, which is indicative of kinetic and diffusive mix mechanisms. And kinetic models are necessary to explain the mix yields and the temperatures that we actually observe in these experiments. So as a primer of what exactly ICF is, in laser-driven ICF, lasers are used to implode a capsule to high enough density and temperature to achieve fusion. I have a little animation here. We have a capsule surrounding some fusion fuel. You get some lasers that are incident on that capsule. It ablates the outside of that capsule, which by Newton's third law creates a force that compresses the capsule inward, and it adiabatically heats and gets really hot until you get fusion. So as this capsule is imploding, you can get mix of materials from the shell into the hot spot in an atomic level, so the atoms are actually, completely mixed together. And that can result from several different mechanisms depending on the collisionality of the fluid. If you have a very non-collisional fluid, particles of one type just stream through the other one, and the displacement you get after some time t is just proportional to that time times the thermal velocity. Whereas if you have lots of collisions going on, you'll undergo a diffusive type of transport, where basically the particle is going through a random walk, and the RMS displacement of the particle after some time is proportional to the square root of a diffusion coefficient times the time. Then finally, you can get hydrodynamic mix, which is basically if you have differences in density between interfaces, then those can get amplified with time according to some growth rate, and then that will create this turbulence that brings things to smaller and smaller length scales until one of these other two mechanisms takes over. So the decreasing collisionality for particles in the tail of the ion velocity distribution in plasmas allows for kinetic transport of those particles even if the bulk is fairly collisional. So what I mean by that is I have a long-range force that mediates interactions in a plasma, the Coulomb force, and that actually leads to your collisionality being proportional to 1 over the velocity between the particles cubed. And that you can compare that to what you expect in like a neutral gas, where the collisionality is actually proportional to the velocity. So it leads to interesting things where if you calculate how the thermal particles, or like the particles at the thermal bulk of your distribution behave, you expect them to behave collisionally, but the particles way out in the tail might actually not be behaving collisionally, and you need a kinetic approach in order to model that. So an experimental campaign has been conducted to study kinetic and diffusive mechanisms using separated reactants with a buried layer. I have some diagrams of these experiments up here. On the right is the control experiments, which is basically just a standard plastic capsule. We use a D-helium-3 fill, so our main fusion reactions you get out are DD protons and neutrons and D-helium-3 protons. And then on the left, we have the separated reactant that we capsules that we compare to, where we embed this deuterated layer inside of the CH capsule. And so when you get D-helium-3 protons out, it must be from that shell mixing into the gas. So hydrosimulations of this campaign predict a marked transition in the regime to more laser burn through, and hotter shells as the shell thicknesses decrease, which you might expect because more of the shell gets blown away. This is a plot of the mean free path of the deuterium inside of this deuterated layer as a function of time for a couple different total shell thicknesses of these capsules. And you can see as we go to very thin capsules, like the 6-micron ones we actually used for the shot, you expect the mean free path of that deuterium to get quite long, on the order of a micron, which is similar to the amount of the depth that this buried layer is in the capsule, and so you expect kinetic effects to become quite important. So going to some actual data from this experiment, X-ray shell trajectory data demonstrates that the control and separated reactant implosions behave in an overall comparable manner, so we can do some actual apples-to-apples comparisons between the two because they're behaving the same. So this is just taken from a super fast camera, essentially. You can see how the shell's moving in. We also have it plotted versus this fall line here, which is just plotting the shell at its peak velocity as it comes in, as well as the D-helium-3 bang time for the control capsules, which is telling you the time when you have your peak nuclear emission. And you can see that D-helium-3 bang time occurs before you actually get the capsule at peak compression. So it's happening when the shock hits the center of the capsule, which is why we call these shock-driven implosions. So for previous thick-shelled separated reactant experiments, hydrodynamic mix that drove them took time to develop, and that shifted the bang time later. This is a plot from a PRL from 2007 where they had these pretty thick, 20-micron thick separated reactant experiments. And you can see that for the separated reactant one, the burn history has a later peak, which is because you don't start getting mix until the shell starts decelerating, and you get these hydrodynamic mix effects that cause it. But in contrast, as I showed on the first slide, for this experiment, the bang time is shifted earlier for the separated reactant experiments, which is indicative of diffusive and/or kinetic mix. Now, if we do some 1D simulations with the diffusion model, they predict markedly less mix than a hybrid ion kinetic simulation that takes into account the non-collisionality of particles in the tail that I was talking about earlier. You can see on the left here, we have some number density profiles at bang time for a diffusive simulation using the Los Alamos X-ray, and on the right is a very similar thing using this kinetic code IFP, and you can see you get the deuterium moving much more into the hot spot, or into the center of the experiment, and so that's essentially saying kinetic effects give you more mix. And this leads to a vast improvement in the comparison of predicted nuclear yield to the experiment, which I have here in this little table here looking at the D-helium-3 proton yield. You can see the diffusive model when you analyze it with something called a fall line analysis. The yield you get is orders of magnitude smaller than the experiment, whereas the kinetic model is within a factor of 2. So we also had some other set of experiments where we incorporated high Z dopants into the shell. So what we've done here is, in our CD, we've included 1% titanium, and on the inner layer of the CH, we included 1% germanium dopant. And then for the two different types of shells, we switched the order of these. And what that was able to do is let us look at how these high Z materials mix using X-ray signatures. So the X-ray imaging data from this shot day preliminarily shows more localization of germanium in the hot spot when you put the germanium on the inside, which is kind of what you would expect, but it's actually showing that the germanium mixes into the inside, even though it's even though it has a pretty high Z and thus is pretty collision, or you would expect to be collisional. So the data here that we have is from a diagnostic called MMI, and basically it's a bunch of repeated pinhole images of your shot, but as you go from right to left in this plot, you're imaging an increasing photon energy, so it's also spectrally resolved, which is why you get these vertical lines here. And you can see that for the case where you have the germanium on the outside, you get these helium-like lines, but when you have the germanium on the inside, you also get these Lyman alpha-like lines, which are only possible due to germanium getting into the center where temperatures are higher and you can actually excite that Lyman emission. So some future work and outcomes. I submitted this work as a paper, and there have been several other campaigns that have been spun off of or tied into this one, including looking at how stocks impact the mix in these experiments, as well as using Thompson scattering to look at the actual distribution function, and using this sort of analysis to look at how a high-Z dopant mix would impact some potential NIF experiments where we want to look at certain thulium nuclear reactions. So moving to the second, to the second set of experiments is about measurement of multi-species plasma effects with some ultrafast detectors. So this uses this diagnostic called PTOF. Sorry. That is routinely used for low-yield measurements of the time of peak nuclear emission, and it's been upgraded for burn width measurements. We have some ultrafast detectors that make this possible, and these ultrafast detectors have been used to perform a measurement that confirms the impact of multi-species plasma effects in Hall ROMs. So PTOF utilizes a biased CVD diamond to measure neutrons, charged particles, and X-rays via the current generated from freed electron hole pairs. I have a picture of what the detector looks like up top, as well as how it fits into the snout, which is what actually goes into the target chamber at the NIF. And then the bottom is just a little schematic showing the mode of operation. Sorry. So the PTOF impulse response functions, or IRFs, have been measured at the 10 Hertz rep rate megaray electron facility, electron accelerator facility at Livermore. So basically what you have here is electrons come out of the accelerator through this beryllium window. They go through a Rogowski coil where we can measure the number of electrons that we have, and they hit the detector. And that detector, the signal goes through a bias T and into our scope here where we read it out. And this facility gives us 5 picosecond bunches of 30 MeV electrons, so we can really make sure we're looking at that impulse response, because 5 picoseconds is quite short. And in these megaray calibration experiments, it was established that certain single crystal detectors have an ultra-fast response, which we show on top. The total width of the signal is only about 200 or so picoseconds. And that's about half as wide as the previous set of polycrystalline detectors that we were using in the past. So this allowed low-yield burn history measurements, which have been validated against the gamma ray history diagnostic, which is another way of measuring burn widths at the NIF, but usually for slightly higher yields. And you can see they match pretty well, except there's a systematic maybe 50 picosecond or so offset that we're continuing to look into. So with all that established, what we've used these for is to look at this experiment N230313, which was a novel NIF shot diagnosing stagnation of flows in the Hall ROM. This uses what's called indirect drive, where instead of the lasers directly hitting the capsule, they hit the inside of this gold can called a Hall ROM, and it basically turns it into an X-ray oven, and those X-rays are what ablate the capsule. But what happens is where the lasers hit on the wall, you start getting that wall expanding into this gold bubble that pushes inward and acts like a piston. And has some kind of stagnation on the axis, and that can affect how the lasers propagate in the Hall ROM. So you want to know how this stagnation works. And so what they did is they filled the Hall ROM with DT gas, and then if you look at the deuterium-tritium nuclear reactions, you can get some sort of sense of how the stagnation is occurring. And what they found is that multi-species models tend to show that the stagnation of flows disassembles more quickly if you take into account like the actual separate species in your plasma rather than acting like they're all one averaged ion, which is usually how the analysis is done. And that's seen by comparing the burn histories where a single species hydrodynamic model is blue and the multi-species hydro model is orange. And you can see that you get this longer tail with the single species model because it takes longer to disassemble. And then we compared that to an experimental value measured with PTOF using these ultra-fast detectors, and you find a very great agreement between the multi-species model and the PTOF data that we measured. So for the future work and outcomes, this was recently published as a PRL showing this measurement, and a new project is underway to probe how dopants and temperature affect the performance of these diamonds. And with that, I'm ready for questions.